Hey Al, how y'all doing? So I've waited the appropriate amount of time. Maybe we should just dive right in. Uh, one thing I want to mention by way of announcement right away, the lab groups that are for the first lab, I have not completed setting them up yet. I'm going to do that right after class. And so if you're in a lab group, which is most convenient to meet between 5 and 7 p.m. tonight, you'll figure out which lab groups you're in because it'll when the assignment will have the group of people in there, but you can contact the other people. Look about 5:30 is what I'm saying, and the lab groups should be available as of then. And if there are any questions, send an email. Administratively, however, you may have some questions. And so administrative questions first would be wonderful. Any questions on things related to turning stuff in or exams or timing?
I missed that one yesterday, for because I was moving things around and driving, but what did I miss out on?
Well, we're going to start. Well, yeah, yesterday we went over basically the syllabus to make sure we're all on the same page. And if you were able to watch the video on Canvas last night or this morning, you should be good. If not, it's all in the syllabus, and you could look that over the syllabus and then watch that at some point in time. But there should be nothing really surprising. We also sort of closed out the day by talking about comparing two groups' means with a confidence interval or hypothesis test. But that was really setting the stage for what we're doing today. Today is also review for anyone who took any prior stat class. You should have bumped into a t-test or a confidence interval for the difference of two population means. And sort of we're going through that today. Again, I call it review, but you could call it what you want. I'm going to say it's sort of like setting the stage for what we're going to do in chapter one, analysis of variance. So Amanda, I think that answers your question, but anyone want to revise Amanda's question or follow up on it? Okay, how about any other administrative questions in nature? Okay, so I'll be sharing a screen with y'all and we'll see how this goes. Earlier today, it turns out that my device that I use for writing on the screen crapped out and got it fixed, but we're just going to hope and pray that it works out fine today. So we talked last time about a box model to compare two different population means. And so let me start by sort of revisiting what that box model is. And let's go with dark blue. We've got these two boxes out there. We'll call one population one, and the other could be called population two. And from each of these two populations, we'd like to take a sample. So we're going to take a sample from population one. So that's the sampling process. And population two also gives a sample. And like we saw in that previous stat class, you probably said, okay, we have things like an average y bar. Well, because it's from population one, we'll call it y bar one. A standard deviation, a measure of spread, I'll call it S1. And N1 is just the number of individuals that we sampled. In that same sense, we've got y bar 2, the mean from population 2, or sample 2, S2, the standard deviation for sample 2, and N2, the number of individuals taken from that sample, from that second population to form our second sample. And what we really have here is just this belief that our sample means, which I'm now going to switch colors and say, aha, y bar 1 should be close to a population mean mu 1. Y bar 2 should be in some sense close to mu 2. If we sample in a fair way from the population, there's no reason to think the sample mean would tend to be higher or lower systematically than the population mean. So we could use the sample means to estimate the unknown population means. And in that same sense, you could say this first sample standard deviation and the second sample standard deviation, S1 and S2, could be viewed as estimates of the unknown population standard deviation. In that earlier stat class you took, and you are from a wide variety of previous stat classes, but in that earlier stat class that you took, you probably learned that characteristics of the population you're sampling from and characteristics of how you conduct your random sample have an impact on how well you can use the sample mean, standard deviation, and sample size from each of the two groups to estimate an unknown population mean for either group, or even in this case, the difference of the two population means. And that's what I'm going to sort of focus on right now is the concept of what if we want to estimate mu1 minus mu2? Maybe in the context of a particular problem, it would be helpful. So let's get back to our catfish from yesterday. Data. You know, might already have the catfish data set open already. So that would be nice. Cool. I've got not. Okay, here are my data. And I apologize for the pink thing because that corresponds to, you know, what I was doing notes. So let's move our friend over here. Here's our data set. I've got information about blue catfish, BCF, and channel catfish, CCF, in the form of two relatively large samples. And I might believe that somehow the sample mean for the blue catfish, the average length, and the sample mean length for the channel catfish will give me a sense for how much longer the one species is than the other. I'm going to go ahead and do analyze. I'm going to just analyze distribution, and you'll see in the lab activity for the day, analyze distribution is just one of the multiple tools that we could be using. But if I say I would like to know about the lengths based on each of the species, for each species of the species, I'm saying, please consider this one. I'm going to calculate information about the length, and you see given to you, I'm going to stack it up. You're going to see, I apologize for the pink. You know, I could remove the pink. Oh, well. Yes, done. We could see that the blue catfish here, we have an average length of 347 millimeters. For the channel catfish, we have an average length of 321. And if I asked you about how much larger are the blue catfish than the channel catfish on average, you might say, well, you know, 347 minus 321, you're going to guess like 26 millimeters on average. I mean, would that make a lot of sense? Use the first sample mean to estimate the first population mean. The second sample mean could be used to estimate the second population mean. Essentially, you're saying you would want to estimate, okay, and no erasing, but rather draw. Okay, so and pick the color. We want to estimate mu1 minus mu2 by, or with, better yet, with y bar 1 minus y bar 2. Yeah, literally the difference of the sample means is a good way of estimating the difference of the population means. I'm making an aside comment, so maybe I should lean over here to the side. That's if you're sampling in a reasonable way. There's no guarantee that you are going to be sampling in a totally unbiased fashion. In fact, with this data set, there's reason to believe that we're more likely to see larger fish than smaller fish in the data set. I'm not going to go into that for now. I'm going to say in the intro stat classes, we deal with a situation where we're saying we're sampling in a fair way from the population. And in a later class, we can double back and say, okay, how do we doct up our method to account for maybe an unequal sampling rate? Yeah, literally, if larger fish are easier to see than smaller fish due to the method of fishing, we might want to correct for a bias, okay? But essentially, you're saying, I have this number I'd like to know the value of for the James River as a whole. How much larger are the blue catfish than the channel catfish? I would want to know that number. I, however, get the difference in the sample means, but that's an estimate. And with every estimate, like in that past stat class, we would love to attach a margin of error, okay? So yeah, literally our confidence interval, CI for confidence interval, for mu1 minus mu2, a confidence interval for how much larger the one species is than the other on average, it would be our estimate, y bar 1 minus y bar 2, plus or minus some number, and I'll call it now 2 standard errors. And that's the standard error for y bar 1 minus y bar 2. Let's talk about this a little bit. Y2. 2 standard errors up and down is approximately 95% confident. If you use the software as I suggest you should use, it's going to calculate literally a value for you, not 2. It will give you a T. Okay, switching colors. It will give you T number of standard errors up and down. The T distribution, it's a number where perhaps from that past class, you just found a value from a table or there was a app lookup. I'm just going to say the software will handle it for us. But the T value is based on 2 things. One is the level of confidence. And usually we're going to go with 95%. So I'll put it within a parenthesis because, yeah, it's in general the level of confidence, but most statisticians, most practitioners, okay, will talk about 95% confidence as the level of confidence they'd like to use. You could be 99% confident if you want to be even more confident. There's a penalty, though, to be more confident of being right. You have to sort of have a wider range of values in your confidence interval. I like it to think about it like this. If you're going into a pet shop and you want that particular fish, and they take the little net out and try and scoop the fish, it takes a lot of time and effort to grab exactly the one fish that you want. If, however, you have a higher level of confidence, a bigger net, you just sort of scoop once and you're for sure to get the fish that you want. Okay? A larger margin of error will go with a higher level of confidence. So level of confidence, that's what you set. In this class, 95% confidence is the value you should be using unless there's a reason that in your discipline, you say, oh, I want to be 99% sure or only 95% sure. That's fine. Go with the stated level of confidence, or more likely just plug in 95% confidence. That's what people do. And also it depends on a second thing, and that is called degrees of freedom. And we'll give you an equation in a little bit to deal with degrees of freedom. Let's just say in this class, it's pretty much automated, the degrees of freedom, okay? So you don't really have to worry about it, whereas in a past class, you might have had to do a little bit of fussing about degrees of freedom. Okay, that standard error, that second portion of the term, and let's go with maybe an orange color. The standard error has something to do with how much data you do have from each of the 2 populations, the sample size, if you will, but also has something to do with how much variability there is in each of those 2 separate groups. The standard error for the difference of the 2 sample means is the first sample standard deviation squared over the first sample size plus the second standard deviation, the second sample's standard deviation squared over the second sample size. So these are numbers that you could with GMP, you could say, okay, I can spot the 2 means. I can figure out T is about 2 for 95% confidence. It's ballpark close. I could find the standard deviation for each of the groups and each of the two sample sizes. You could do that by hand, and I believe the lab activity asks you to do that by. Okay. Let's clear that and move forward. Okay, so our confidence interval is, like we said, based on the standard error. And there's two ways to calculate that standard error. We gave you this second version of the equation. But if you're presented separate standard errors for each of the two groups in the first place, all you need to do is square them and sum them. Okay. And our equation overall is, yeah, our estimate, okay, estimate of that difference, plus or minus t standard errors. And that's all quite straightforward to find, other than that degrees of freedom. And I'm just going to say this top equation is fun. I never want to do it by hand. And I'm going to say, if life gives you the situation where you would say, I need to know exactly the degrees of freedom, we're going to recommend just taking the smaller sample size and subtracting 1 from it for degrees of freedom. That will give you a degrees of freedom which is smaller than the true degrees of freedom. Thus, your confidence interval will be a little bit larger or wider. It's a little bit conservative, if you will. Okay, so in the context of a data set that you could work out, and let's maybe open this data set up. Okay, here we go. No. Okay, there we go. And these are data from the 1960s, I believe 1967. And the story behind the data is that there was a blackout in New York City, and as one would expect, people can't do anything because you're stuck in an elevator or who knows what. And the New York Times tried to look into the question of whether the birth rate is higher exactly 9 months following such an event as a 3 days without electricity in New York City. And so they started collecting data, about 9 months later, minus 2 weeks, 9 months later, minus 1 week, and then exactly 9 months later. They have about 3 weeks worth of data overall. And they found that there wasn't really a noticeable increase in the birth rate. But one thing they did spot that was interesting, I think, is that the type of day seems to relate to then the number of babies born per day. And so in Manhattan, okay, they calculated the number of babies born on each and every day. I believe that was August 1, August 2, August 3, all the way through August 25 of that 1967. And the type of days, well, so Monday, Tuesday, Wednesday, Thursday, Friday. But when we switch from Friday to Saturday, it switches from a weekday to a weekend day. And perhaps there's a difference between weekend days and weekdays. So to sort of get after this question graphically, I could literally use a tool within GMP Graph Builder. I could say, let's see if the number of births per day seems to be different by the types of day, weekdays and weekends. And it looks as though weekends maybe has a lower number of births per day than weekdays does. And again, each data point is corresponding to an individual day. So average number of births per day is lower on weekends than weekdays, perhaps. So you get a sense for it's less, and I'm ballparking this with my eyeballs, and this is about 375. Here's about 450. My guess is 75 more births per day on weekdays than on weekends. If I want to explore the data using a formal tool, I could use, excuse me, analyze fit y by x. And that's a tool that we're going to be using through approximately chapters 1 and 2. Fit y by x. Analyze fit y by x is the most common tool that we'll use. And yeah, same as before. How does the number of births per day depend on the type of day? Tell me, how does the number of births per day depend on the type of day? The response may be depending on your x variable, your explanatory variable, if you will. I click OK, and we see the same sort of graph as we had seen before. But like with other things in JMP, these little red triangles allow you to turn things on and off. So if I want to look at the means and standard deviations, for example, I could say, okay, click and turn those on, and it gives me information about the average, the standard deviation, the number of individuals, and even the standard error for just the weekdays. Across the 19 weekdays, we have a standard error. Across the 6 weekend days, we have a different standard error. So these data that you could turn on and off, okay, I've did a cut and paste and did a little bit of rounding here. 19 weekdays, 454.5, 22.1 was the standard deviation, or the standard error was 5.1 for weekends, 6 weekend days, averaging 377.3, standard deviation 27.0, standard error 11.0. If I wanted to calculate the standard error using the quick formula, again, the quick formula is taking the separate standard errors, square them and sum them. I could also have taken the individual standard deviations and squared, divided through by sample size, and then added and rooted. But I'm saying I can take my standard errors, 5.1, square it, 11.1, sum it, take a root. Actually, hold on. This looks like the Pythagorean theorem, doesn't it? A squared plus b squared is c squared. There is a connection. I will emphasize that one later this term. Our standard error for the difference of the two sample means is 12.1, meaning we think our difference of sample means is probably within about 12.1 births per day from the difference of the two population means, which is all weekends subtracted from all weekdays, the averages. If I want to use the funky degrees of freedom formula, I could calculate 7.3. But I said earlier, just use 5 degrees of freedom, the smaller sample size minus 1, unless you want to do the work. So we could get our confidence interval pretty quickly. Our confidence interval using 7 degrees of freedom, and that's using a T table. Do y'all want me to show you how to use a T table? Okay. So let me get back into GMP, not GMP, but instead of that. Okay, check this out. Our friend here. Oh man, I didn't have a direct link to it there. Okay, so is it in this section? Hope. Okay, I don't have that lying around, but I do somewhere else. There was a JMP probability distribution calculator. And do you see the word calculator? Let me search for it over here, and I'll put a link to it inside Canvas. Okay. Okay. Okay, yeah. Okay, that's frustrating for me. Okay, I don't have this lying around, and I think it should be there somewhere, but let me try one more time. This is so frustrating for me. I think it's almost certainly on my other computer, which doesn't help right now. Okay, so I will later put a link in there for y'all for this week. But the upshot really is you could use a normal table to get a value, and it's not really necessary to tackle the lab problems or the homework tonight. So I don't feel too badly about it, but I really wish, because that would have been slick. Okay. So I'm just going to say, yeah, you could plug in the two separate means, y bar 1 and y bar 2. The standard error, you could plug that in, and you just have to know how many standard errors to go up and down. And we said the answer is about 2 if you want 95% confidence. Based on the degrees of freedom being 7, I would use 2.365, or if you just plugged into on a homework set, you'll get at most a little tiny bit off. On a test, at least, no more than like 1 point off out of 5 or 6. And so if you are running late, don't have the ability to use the software, and somehow can't get an exact T value, just plug in 2 and everything should be nice. So our procedure will give us 77 plus or minus 28. If I did a quick rounding and subtracting and then adding, I have approximately 50 to 105. Okay. So in other words, I'm 95% sure that the number of bursts on weekdays minus the number of bursts on weekends is the range 50 to 105. Rephrase that. I'm 95% sure that weekdays have 50 to 105 more bursts per day on average than weekend days do. If you're trying to interpret a confidence interval, using a word like more or less is really helpful. It clarifies the question. Tell me which group is more and which one is less. I could say that weekends have 50 to 105 fewer births per day on average than do weekdays. It's not really hard, but you guys need to get in practice of doing that. So that's the nature of the first couple exercises and some of the content that we're going to be doing in the first couple weeks, dealing with words like more or less correctly. Okay, we'll more or less use the words more or less correctly. Any questions about a plug and chug approach? You've all seen this. You can do it by hand. Hey, let's just go ahead and get the software to do the whole thing for us. They and type. We said, okay, you could turn on things like means and standard deviations. You might have noticed it also allows you to do this thing called a t-test. We haven't formally talked about the t-test yet. We will do that a little bit today. But you guys had the t-based confidence interval just now. The test procedure does the confidence interval as well as the test. I click OK on that. And we see additional output down below. And JMP is sort of nice because you can take things and resize them if you want to make it fit the form that you'd like it to fit in. But I'm saying here in my t-test, I have my confidence interval, the upper and lower confidence interval. The upper value is negative 49. The lower value is negative 106. And it's for week end minus weekday. And if I tell you I'm 95% sure that the number of bursts on weekends minus the number of bursts on average on weekdays is negative 50 to negative 105, you could just flip the order here and say weekdays minus weekends is 50 to 105. When in doubt, if you're struggling with interpreting a confidence interval, literally just change the sign by changing the order of what's subtracted from what. And it usually gets easier when you use words like more or then less. Any question about interpreting that? 95% sure that the average number of bursts on weekdays is 105 to 50 more than on weekends.
Is there a way to change the weekend and weekday on JMP, like manually?
The order?
Mm-hmm.
Yeah, there is. Great question. And because it will matter a little bit later, I might as well mention exactly right now. So it alphabetically said WEEKE and WEEKD. It's sort of chosen order for weekend versus weekday. You can set the order you want. So if you click on a column up at the column header, okay, so the variable week type or day type, I'm going to click down in the column header, and I'm going to right click on it. And so if I go down to column info, okay, column info. No, I'm sorry, that was wrong. Right click on it, and I go to column properties. You know, oh, column properties was up at the top. So under column properties, so under column, right click on it, under column properties, say, okay, the value order. So software basically says, I got to put someone first. Who would I put first? If you don't specify who you want to be group one, it will choose a group one for you. So via column properties, value order, you could say, okay, well, it's chosen for me weekday, and then weekend. It said weekend will be listed first and weekday second. You naturally compare it to the first group. If we take weekend and move it up above weekday and click OK, and then redo the same analysis, analyze fit Y by X, I'm going to hit the recall button because that's always quick to get things redone exactly as before. And I'm going to turn on my, excuse me, turn on my t-test. And you're going to see here it's weekday minus weekend, the exact opposite of what we had before. So weekday minus weekend, weekend minus weekday. But the numbers, shoot, it's like 77 negative as opposed to 77. We had a 12, 12, we had 105, 105. Yeah, you can get the software to do what you want, but most people would say, all I need to do is to change the signs of the difference in the upper lower end for the difference, and even change the sign for the t ratio if we're talking a hypothesis test. So it's not a big deal, but at a later point in time, we might have multiple different levels rather than just weekday and weekend, two groups. And it may become important to sort of pick which group you want to be, for example, listed last. So I'm glad you asked the question. Thank you. Let's maybe move forward a little bit, unless one of you has another question right quick. Okay. So what's the difference between a hypothesis test and a confidence interval? They answer really similar questions. A confidence interval really tries to answer the question, what is the value of mu1 minus mu2? Oh, and put in margin of error on your estimate. So the plain English question is, hey, tell me how much higher the number of births is on weekdays than weekends. Tell me a number. A hypothesis test always will give you a yes or no question. For example, is the number of births on weekends different from the number of births on weekdays? It's going to be a yes/no question. Or perhaps you would want to phrase it a little bit more carefully. Now that you've already looked at the confidence interval, you might want to say, is the number of births per day on a weekday higher than the number of births per day on a weekend? One-tailed versus two-tailed test, or directional versus non-directional, if you will. We're not going to really have to fuss about that just yet. I'm going to say focusing on the key is your natural question will lead you towards a confidence interval. If you want to estimate something, confidence interval. If you want to test a hypothesis, use a hypothesis test. And in any hypothesis test, there's 1, 2, 3, 4 parts. I'm going to phrase it as 4 parts, but you could say 5. I've seen some books saying, oh, you have to do 8 separate things for a hypothesis test. Other books, only 3. I'm just going to say, here you go. You have to tell me in advance what you're comparing. What are the 2 hypotheses you're going to compare? At the end of the day, you have to say yes or no to the question. Tell me what the yes is. Tell me what the no is. And you do that before you even look at the data. Second thing, choose a level of error that you're willing to accept. Sometimes it's called the level of the test. 0.05 is traditional. It's going to correspond sort of like a type 1 error rate of 5%. If you're not remembering type 1 versus type 2 error, no big deal. We'll hit that in a bit. It's also sort of comparable to a 95% confidence interval, because a confidence interval is 95% likely to be right would be wrong about 5 out of 100 times, an error rate of 5%. So an error rate of 5% is really pretty common. Third step, calculate a test statistic. A test statistic is literally just a way of measuring how close your data are to matching the null hypothesis. You could say it's also how far your data are away from matching the null hypothesis. I mean, if I'm looking at two people in a room, could I say, oh, how close are they? Oh, they're about 4 feet apart. Or I could say, how far apart are they? You'd say they're about 4 feet apart. The two questions are just plain English ways of saying the same thing. Okay. A test statistic is just a way of measuring how close the two means are to the hypothetical values of the two means. And then second, right after that, we calculate a p-value. If you haven't seen a p-value before, it was in your prior stat class. We'll hit a lot of p-values this term. A p-value is just a recasting of your test statistic across multiple ways of doing hypothesis testing, such that the p-value always has the same interpretation, regardless of the specific method you're using. So it's like a way of, let's just convert into standard units, p-value units, and then you hit your conclusion. Okay, so let's go ahead and talk about another question, which I think is not so interesting, but is well, maybe a little bit interesting. And let's get the data for these data. Okay. I for ice cream. Looking for the ice cream. Okay, there we go. Okay, I've got data here on a variety of ice creams sampled by Consumer Reports in 1993 from major market grocery store chains and their major brands. And so you might be thinking, well, you know, that's not really sampling in a random way from the population of possible ice creams, but we do have a fairly representative sample of the things that aren't locals. Okay, so you've seen Breyers, you've probably heard of Ben and Jerry's. You might not. ShopRite, probably not. Newman's Own Vanilla, years ago they had it. There was a grocery store in Texas that had Bluebell as a variety. Turkey Hill, Publix, Florida-based chain, Albertsons. I guess Albertsons and Safeway, now part of the same company or becoming part of the same company. However you want to slice it, we've got a bunch of vanillas. And we got a bunch of chocolates. We get information about the number of calories per half cup serving. And yes, you heard me right. 1/2 cup serving of ice cream is deemed a one serving. 1/2 cup of ice cream is deemed one serving by Consumer Reports. I don't know what they were thinking, because I've never seen anyone eat a 1/2 cup of ice cream and that's it. But I digress. Okay, so here's your question. If you want to say, hey, does chocolate have a different average number of calories than vanilla? That's a yes or no question. So hypothesis test. We have to specify our null and our alternative hypotheses. The null hypothesis always has an equality in it. And so you'd say, oh, well, different, the same. Usually the natural plain English question is not the null hypothesis. So if you take the logical opposite of, hey, is there a difference between vanilla and chocolate? You would have indeed your null hypothesis. mu1 and mu2, vanilla and chocolate, are the same on average. The alternative is a logical negation of the null hypothesis. Literally, you take that equality and replace it with something else, something that doesn't include inequality. Not equal to is, hey, there is a difference. Over here off to the side, if you want to tackle the question, does chocolate have more calories than vanilla? You would put a greater than. Mu1 for chocolate has a greater number of calories than does vanilla, mu2. That's entirely legitimate. It's not a requirement, but usually the plain English version of the question that you have is going to dictate your alternative hypothesis. Okay, so what sort of data would convince us that vanilla and chocolate are different in terms of the average number of calories? I'm thinking if vanilla clocks in as like 140 and chocolate's about 200, you'd say that's a lot. So a large difference in the sample means would be convincing for me that the alternative hypothesis should be believed. On the other hand, if the two sample means are really quite close, I don't have any reason to think the alternative makes sense. Again, you want to stick with the null hypothesis until you're convinced by the data that it's wrong. Okay? So I'm willing to be convinced that the null is wrong. I'm willing to believe that vanilla and chocolate are different on average in terms of the number of calories, but I'm only going to believe that if I see a large difference in the sample means. So, and I'm going to skip over the first bullet point there, but I will sort of get towards the second one. In a hypothesis test, you have to end up believing the alternative hypothesis or the null hypothesis at the end of the day. I would believe the alternative hypothesis. Oh, shoot. I would believe the alternative hypothesis, HA, if we are not likely to have seen data like what we really did see if vanillas and chocolates were the same on average. Let me repeat. If truly vanilla and chocolate have the same number of calories on average, and our sample means were far apart, you'd say, well, that shouldn't have happened if truly the populations were the same. So we have to calculate some sort of measure of how likely or unlikely is this. So if you shouldn't have seen what you did see, if the null had been true, believe the alternative. Otherwise, we'll just say the results are inconclusive. We cannot yet say we have conclusive evidence that the alternative should be believed. Okay? So how do we do the procedure? Well, we said a test statistic is what you need to do next. And a test statistic is just, again, a measure of how close our data are to what we should have seen if the null hypothesis had been true. And our null hypothesis is that the two means, mu1 and mu2, are the same. And I'm going to suggest the following would work. Literally, the difference of the sample means should be 0 if the null hypothesis is true. So in the numerator of our test statistic T, we have that comparison between what the data are saying and what we would likely see if the null were true. And we'll divide through by the standard error, which is a measure of how close the difference of the sample means is likely to be to the difference of the population means. So this will calculate in standard errors how close the two means are to each other. How close are the two means to each other in standard errors? And so that's sort of a hard number to work with, but we want to sort of switch gears and talk about a p-value, okay? And so let's maybe go ahead and finish up here with our vanilla and chocolate. So under analyze, fit y by x, we're going to say, does the number of calories differ by the flavor category? I click OK. In looking at the data here, and maybe I should spread them out a little bit, under display options, if you want to spread them out a little bit, like some might be overlapping, you'd say, oh yeah, jitter them. So I'd see that vanilla and chocolate here look like they're pretty close on average. Maybe chocolate's a little higher than vanilla, but not a lot. Just glancing at these data, I would say I'm not going to probably believe that vanilla and chocolate are different on average at the end of the day. But we could turn on the t-test and we get our calculation of the test statistic T. And maybe I should even turn on the means and standard deviation so you can see that indeed we're plugging numbers into our equation right from our output. So yeah, literally our friend here, chocolate mean 174.7, vanilla mean 165.6, compared to 0, the difference compared to the 0 we should see if the null were true. And our denominator is the standard error for the difference, or the root of S, the first standard error. Okay, so 10.7 squared plus then 8.6 squared. Okay, that will give us the standard error term in the denominator. Or you literally could notice the numerator here is this difference 9.15. And the denominator term over here is the standard error for the difference. -9 over 13.7 gives us our T ratio. Now, here we had chocolate minus vanilla being positive. Here it's vanilla minus chocolate being negative. That is not surprising. That's in fact exactly what you would expect. Okay, so let's get to this thing called the p-value. I think I've got the definition here.
I had one question.
Please.
The T ratio, if it's negative, does that mean that's the difference between the two?
Well, yeah, literally, the T ratio here that we found is positive if you have chocolate minus vanilla. But if you have vanilla minus chocolate, the T ratio is negative because you swap the role of each of these two terms. Does that answer your question?
So yes, but I'm still a little confused. So my understanding of it is that if it's negative when you swap it, then the one that you swap is greater than the other value.
I think what you're saying is correct, but it's also not really what we're focusing on here.
Got
We're
it. Okay.
focusing usually on the size, because this 0.66,
Mm-hmm.
seeing if it was a 0.66 positive, it would be over here. And an
Mm-hmm.
upscale area says, oh, I could have easily seen something like this if the null had been true. If our T ratio is the negative 0.66, like the software says, vanilla minus chocolate, it also is pretty likely that I'd see a difference like that if the null were really true. The
Oh, okay.
p tells us the chance of seeing something like what we did see, or more extreme, in either direction. You know, could vanilla minus chocolate have been more than a negative 0.66 as its T value, or could it have been more than positive 0.66? We're saying, how likely is a difference of this magnitude or larger with our p-value? In this case, our p-value is non-directional, 0.5. I'm saying if truly vanilla and chocolate have the same exact population mean, then half the time I'd see a sample mean that differs by like a 9 or more calories per half cup serving. This 9-calorie difference between the vanilla and chocolate seems like it's tiny. We could have easily seen it just by luck alone. So that seems to be like telling us what we ought to believe at the end of the day. And maybe rather than focusing on that, that's something the lab covers. Let's just focus on what you would get with your p-value of 0.5. It says I could have, again, easily seen something like that if the null had been true. No reason to doubt the null hypothesis of equality. If these two population means were the same, I could have easily seen what I did see. If, however, our p-value, and this is not the case here, but if our p-value had been like 0.003, you would say in only 3 out of 10,000 samples would I've seen a difference between vanilla and chocolate this great. If really vanilla and chocolate were the same, that's a solid reason to doubt the null hypothesis of equality of the two groups. So any questions on that so far? I know we're hitting the about time out location.
So is the T ratio the same as the p-value?
Not the same, but it's what gives us the p-value. And it's like one of those situations where if I tell you, oh, one of my kids happens to be 193 centimeters, 193, yeah, 193 millimeters tall, you'd say, okay, tall or short. A lot of us don't use millimeters for measuring heights. If you convert it into meters, 1.93, you still think, I don't even know what that means. Okay. If I converted to units that you were familiar with, like feet and inches, you'd say, okay, I get it. The T ratio, the T statistic, works with, well, how many standard errors away from the null hypothesis are our data? That's sort of an uncomfortable number to work with, but it can give you the p-value, and sort of like graphically you can sort of see here, this p-value is shown as the two areas shaded taken together. We could have easily seen something like this if the null had been true. The p-value is literally what's the chance of seeing something like this if the null had been true. So it allows us to, well, we compare the p-value to our definition of, is that unusual enough to believe the alternative? And our conclusion is always based on comparing the p-value to the level of test 0.05. If the p-value is below 0.05, you believe the alternative. If the p-value is, like here, not to below 0.05, you stick with the null hypothesis. There's no reason to think here that vanilla and chocolate are different on average. Does that answer your question?
Yeah, so that prob greater than absolute value of t is the p-value then, right?
In this case, yeah.
Okay, got it.
It's based on the T ratio right upstairs. Test statistic, p-value. I use the p-value to hit conclusions, but the test statistic is the way to get to the p-value itself. Okay, it's a good place to stop. Like I said at the beginning of class, what I'm going to do is stop the sharing and the recording, and I'm going to immediately go and finish putting the groups together. And by 5:30, I should have all of the groups properly assigned and thoroughly assigned, so that way you can start your lab activity. If you're thinking possibly 5 to 7 tonight is when you're going to want to do the lab, just look at 5:30 and see what group you've been assigned to, and then reach out to the others in that same group, and you'll get set up. Usually what students like to do for the lab is one of you will download the Word document version, and you'll put it in a Google Doc, and then upload that as a Google Doc, and then share with those also in your lab group, and you'll plow your way through it, answering the questions as you go. Some of you will probably be more focused on using JMP, some more focused on the typing of the answers. Some of you will probably be more focused on cutting and pasting, and you know, whatever it is that y'all are going to play as a role, you all should be involved and agree as you go. Many groups do work with Zoom. Some prefer Discord. It's just a matter of making sure that you're, if possible, synchronously working with your classmates to get the lab done. So if there are no more questions, I'm going to stop the recording.